What if the universe is full of habitable worlds and we can never reach a single one of them? That's the question nobody in astronomy wants to answer, because the math says something uncomfortable. The nearest potentially habitable exoplanet orbiting a Sun-like star is Kepler 22b, 640 light-years away. At the speed of our fastest spacecraft, the journey takes 9.4 billion years. With the most advanced theoretical propulsion ever designed, it still takes 5,300 years. Tonight we're going to trace that journey from beginning to end. We're going to find out what Kepler 22b actually is, why it's probably not what you were told, and why the space between here and there might be the most dangerous environment a human being could ever enter. So settle in and get cozy. This one goes places you won't expect. Part 1. The discovery that changed everything. Imagine standing in a press room in Washington, D.C. on December 5th, 2011. Fluorescent lights hum overhead, journalists fill the seats, cameras are ready. And then a scientist steps up to a microphone and says something that would ripple through human consciousness for years to come. We have found a planet in the habitable zone of a sun-like star. Not someday, not theoretically. Now. It exists. It's real. We've been looking for something like this our entire history, and we finally found it. The planet's name was Kepler 22b. The media would call it Earth 2.0, Earth's twin, a second Earth. And for a moment, just a moment, it felt like humanity had been handed a second chance at civilization, a backup plan written into the fabric of the cosmos itself. But before we get to why that's almost certainly not true, we need to understand how we even found this world in the first place, because the discovery itself is a story worth lingering on. 2 years before that December press conference, in March of 2009, NASA launched a space telescope called Kepler. It wasn't the biggest telescope ever built. It wasn't the most powerful. What made Kepler revolutionary was its mission: stare at the same 150,000 stars continuously for years, waiting for the infinitesimal dip in brightness that would signal a planet crossing in front of its host star. Find enough of those dips, and you have proof. A planet exists. This is the transit method, and it changed everything about how we search for worlds beyond our solar system. The telescope pointed at a region of sky called Cygnus. It contained about 500,000 stars, but Kepler narrowed its focus to 150,000 of them. If you think about what that means for a second, it's staggering. A single telescope, looking at a pinprick of sky, observing 150,000 individual stars with the patience of a machine that doesn't sleep and doesn't lose focus. Year after year, Kepler collected photons. It measured the brightness of those stars with a precision that, frankly, seemed impossible before we actually did it. And something extraordinary happened. Planets started to emerge from the noise. The discovery of Kepler 22b was formally announced by William J. Barucki and 82 co-authors. Think about that number for a second. 82 other people. The paper appeared in the Astrophysical Journal, volume 745, page 120. And what it described was the confirmation of a world around a star designated Kepler 22, found through the observation of 3 planetary transits, each one lasting 7.4 hours as the planet slowly crossed in front of its star from our perspective. Here's what makes this so important. 3 transits is the absolute minimum to claim a confirmed discovery. You need at least that many to rule out false signals, to distinguish a real planet from instrumental noise, or a star spot, or any of 1,000 other things that could trick you. Kepler collected photons patiently enough, precisely enough, that astronomers could say with confidence, yes, this is real. A planet is there. It has a period of 289.9 days. It orbits a yellow dwarf star every 9.5 months. The star itself is worth understanding because it tells us something crucial about why people got excited. Kepler 22 is classified as a G5V. which is just 2 steps away from our Sun's classification of G2V. It has a surface temperature of 5,518 Kelvin. The Sun, by comparison, is 5,778 Kelvin. Kepler-22 is about 97% the mass of our Sun. It's only 79% as luminous. It's an older star, somewhere around 7 billion years old, which means it's been burning hydrogen for roughly 2.4 billion years longer than our Sun has. A star like this, scientists knew, was exactly the kind of star where you might expect to find something interesting orbiting it. And the planet's position only made it more intriguing. Kepler-22b orbits at a distance of 0.849 astronomical units from its star. An astronomical unit is an astronomical unit, the distance from Earth to the Sun, so this planet is about 15% closer to its star than Earth is to ours. Under normal circumstances, that would mean the planet would be scorched. Too close to the host star would mean too hot for life, or at least for life as we understand it. But Kepler-22 is dimmer than our Sun. Its reduced brightness means that even though the planet is closer, it receives about the same amount of radiation that Earth does. The math works out. The planet sits in what astronomers call the habitable zone, the region around a star where liquid water could exist on a planetary surface, where temperatures might support life. The equilibrium temperature, assuming the planet had an Earth-like greenhouse effect, was calculated to be around 22 degrees Celsius, room temperature, the kind of number that makes people dream, the kind of number that makes you think, yes, someone could walk on that surface and not need a spacesuit. They could breathe air that came from that world, if that world even has breathable air. They could drink water from that world if the water were clean. They could live there, maybe. They could call it home. That's what the headline seized on. Earth's twin. Earth 2.0. A second Earth waiting out there, ready for us, wanting us to come find it. And in that moment in 2011, the world held its breath a little. But here's where you have to understand something fundamental about how hope works in astronomy, and maybe in science generally. When you find something new, you find it in the shape of what people are already looking for. The media wasn't looking for a super-Earth with an unknown composition, orbiting in the habitable zone of a G5V star. The media was looking for Earth. A second Earth. A backup planet. A world where life was possible. Where maybe life had already started. Where maybe intelligent civilization had already bloomed. The newspapers and the television stations and the websites all read the announcement, and they read the word habitable, and they filled in the rest of the story themselves. And the scientific community, to be fair, didn't exactly stop them. There's a kind of restraint in science, a responsibility not to overstate things. But there's also, inevitably, a hunger for discovery and attention and funding. Kepler-22b was a triumph. It was the first confirmed planet in the habitable zone of a Sun-like star. This was genuinely historic. And in the rush to celebrate that achievement, something got lost. The planet became a symbol for something larger than what it actually was. Because here's the thing that nobody shouted about on December 5th, 2011. We didn't actually know what this planet was. We still don't. 15 years later, we still don't. We know it exists. We know where it is. We know how long it takes to orbit its star. But we don't know what it's made of. We don't know what it looks like. We don't know if it has an atmosphere. We don't know if there's water on it, or if it's a barren rock. We don't know any of the things that actually matter. And that's the open loop that leads us into the second part of this story, because the reason we don't know those things is that Kepler-22b is unimaginably far away. So far away that it might as well be unreachable. So far away that the distance itself becomes a kind of character in this story, a force that shapes everything about whether this world, however habitable it might be, will ever be anything more than a name in a catalogue and an idea in someone's imagination. Part 2. The Lie of Earth. 2.0. When you look at the actual data for Kepler-22b, the first thing you notice is its size. The planet has a radius of 2.38 times the radius of Earth. That's not a small difference. That's not a detail to gloss over. That's the whole story right there if you know how to read it. Think about what radius means. If something is twice as wide as Earth, It's 8 times as voluminous. Kepler 22b is 2.38 times as wide, which means it has roughly 13 times the volume of Earth. That's a planet that's fundamentally structurally different from the world we live on. And the implications of that difference cascade outward from there. Here's the thing about exoplanet science. We can measure a planet's radius with remarkable precision, using the transit method that Kepler used. When the planet crosses in front of its star, the amount of light that gets blocked tells us exactly how big the planet is. It's almost geometrically simple, but measuring mass is infinitely harder. Mass requires something called radial velocity detection. Essentially, the planet's gravity pulls very slightly on the star, causing the star to move toward us and away from us at minuscule velocities. Measuring those velocities requires a spectroscope sensitive enough to detect shifts in starlight that are smaller than walking speed. From 640 light-years away, this is almost impossibly difficult. And for Kepler 22b, we've basically failed to do it. We have an upper limit on the planet's mass. It's no more than 9.1 times Earth's mass, but that's just an upper limit. It could be much less. It could be half that. We don't know. And that uncertainty matters more than you might think. Here's why. A planet's radius alone doesn't tell you what it's made of. This is a problem called mass-radius degeneracy, and it haunts exoplanet science. Imagine I tell you that a spherical object has a radius of 1 meter. Can you tell me what it's made of? No. It could be a ball of lead. It could be a ball of foam. It could be mostly hollow with a thin shell. You need more information. You need mass. Mass and radius together give you density, and density tells you composition. Kepler 22b has a radius that's 2.38 times Earth's. For Earth, that radius coupled with Earth's mass gives us a planet that's mostly rocky, with an iron core, with continents and oceans and crust and mantle. But Kepler 22b's radius, combined with an unknown mass somewhere between 1 and 9 Earth masses, gives us a bunch of possibilities. And almost none of them are actually Earth-like. The most likely scenario, based on what planetary scientists understand about how planetary systems form and evolve, is that Kepler 22b is either an ocean world or a mini-Neptune. An ocean world would be a planet almost entirely covered in water, with an ocean hundreds of kilometers deep. A mini-Neptune would be a smaller version of Neptune, with a thick atmosphere of hydrogen and helium surrounding a rocky core, or possibly a liquid water interior under all that gas. Neither of these is something that looks or works like Earth. If it's a rocky super-Earth, that's actually been ruled out to pretty high statistical confidence. The radius is too large for a purely rocky composition. You'd need to pack so much rock into that volume that it would be denser than anything that actually forms in nature. So you're left with something else. Something with water, something with volatiles, something fundamentally different from our world. And here's the crucial part. If Kepler 22b is an ocean world, if it's a planet with an ocean hundreds of kilometers deep, there's no surface to stand on. There's no beach. There's no land. There's just water, descending down and down and down, until you reach a layer so deep and so pressurized that the water transitions into exotic forms of ice. Ice 7, Ice 8, Ice 10, forms of solid water that only exist under pressures found in the interior of planets. The bottom of that ocean would be completely black. No sunlight would reach it. The temperature might vary, but it would be cold and dark and crushing, and we still don't know what kind of atmosphere, if any, exists above that water. Maybe there's a thick, steamy envelope like Venus, with clouds of water vapor and a greenhouse effect that makes the surface temperature scorching. Maybe there's a hydrogen-helium atmosphere like the gas giants in our solar system. Maybe there's no atmosphere at all, and the water is exposed directly to space. We don't know. We literally cannot tell. The James Webb Space Telescope, the most powerful space telescope humanity has ever built, is designed to analyze the atmospheres of exoplanets. But it's busy with closer targets. TRAPPIST-1e, which orbits a red dwarf just 40 light-years away, has already been observed. Proxima Centauri b, just 4.2 light-years away, is a priority. Kepler 22b is 640 light-years away. It's not even on the list. This is where the title of this part becomes relevant. The Lie of Earth 2.0. Because Earth 2.0 implies Earth-like, it implies rocky. It implies continents and oceans in Earth proportions. It implies something you could stand on, something you could walk across, something that resonates with the world we know. And Kepler 22b in all likelihood is none of those things. The media used a metric called the Earth Similarity Index, the ESI. It's a number between 0 and 1 that attempts to quantify how much a planet resembles Earth, based on orbital position and planetary radius. Kepler 22b scored 0.90. That's very high. But TRAPPIST-1e, which is a far more promising candidate for actual habitability, scores 0.95. Kepler 452b, which orbits a star 1400 light-years away, has an ESI of 0.83. Proxima Centauri b scores 0.94. The ESI is a useful tool, but it measures one specific thing: how much a planet's orbital distance and size resemble Earth's. It does not measure whether you can breathe the atmosphere. It does not measure whether you can drink the water. It does not measure whether life could emerge there, or whether life has already emerged there. It's a mathematical comparison of parameters, dressed up in a metric that implies more than it actually tells you, and that's the real crisis of exoplanet discovery right now. We can find planets. Kepler found over 2,600 of them. We can measure their orbits. We can measure their sizes. We can even, for the closer planets, start to measure their atmospheric composition. But for most exoplanets, we know almost nothing about what actually lives there, or could live there, or what actually exists on the surface or in the clouds. We see a name in a catalogue. We see some numbers. And then we imagine the rest. We imagine Earth. We imagine life. We imagine that the universe is full of worlds like ours, waiting for us, ready to welcome us. But here's what you really need to understand about Kepler 22b, and this is the thought that should genuinely settle in your mind as we move forward. Even if it were a perfect Earth analogue, even if it had breathable atmosphere and liquid water oceans and continents and everything you could possibly want, the distance to get there would still be almost impossibly vast. The distance would still dominate the story, and in a way, the distance is the real character in this narrative. The distance is what makes Kepler 22b meaningful, and also what makes it tragic. Because 640 light-years isn't just far, it's far in a way that breaks human intuition. Part 3. A world of water and silence. Let's imagine something for a moment. Let's say that Kepler 22b is an ocean world. Let's say that's what we find when we finally get the atmospheric data, when we finally know enough to paint a picture. 2 to 5 Earth masses. A significant fraction of that mass is water. The ocean covers the entire planet hundreds of kilometers deep, perhaps as much as 500 kilometers from surface to bottom. From our vantage point, if we ever got close enough to see it, this planet would look almost completely blue. But the light hitting that world would be different from the light that hits Earth. The star is dimmer, remember. Kepler 22 is at 79% of the sun's luminosity. That means the light is softer, warmer, more muted. No harsh shadows, no brilliant whites. Everything's suffused with a gentle amber or orange glow. The sky above the ocean would be a different colour than Earth's sky. Maybe it would be more orange. Maybe it would be hazy with water vapour. Maybe there would be clouds that never break, that rain down endlessly into an ocean that never fills or empties because the cycle just continues, perpetually, on a world with no land to interrupt it. There would be no continents on this world, no mountains, no valleys, no places where the crust breaks through the water and creates boundaries between the sea and the dry land. Just water and sky, the horizon meeting in an endless circle. Wave motion driven by storms in the atmosphere. Currents stirred by the planet's rotation and the heat from the star, and maybe, if the planet had any residual internal heat from its formation, warmth rising from the depths. But nothing solid beneath the waves that you could stand on. Nothing you could build on. Nothing you could claim as ground. The ocean floor, if you could ever reach it, would be smooth. Not like Earth's ocean floor, which is carved and shaped by geology, by plate tectonics, by the constant grinding and spreading and collision of rocky plates. Kepler 22b doesn't have plate tectonics, at least not the kind Earth does. The ocean is just water, getting denser and stranger the deeper you go, until eventually it transforms into something that isn't quite ice but isn't quite liquid either. Ice 7, perhaps, which exists at pressures around 1 gigapascal. As you go even deeper, maybe Ice 8 or Ice 10, forms that only exist at pressures found nowhere on Earth, nowhere in our solar system except in the cores of gas giant moons. The transition would be gradual and continuous, pressure and temperature and the molecular structure of water all changing together, until the concept of a surface or a boundary breaks down entirely, and you're just in the interior of a planet dense and dark and alien. The surface temperature of this world would be regulated by its atmosphere. We don't know what that atmosphere is, remember? It's one of the great unknowns. If it's a thick atmosphere, with lots of carbon dioxide or water vapor or other greenhouse gases, the temperature could be high. If it's a thin atmosphere, the temperature could be low. The equilibrium temperature calculated for the planet, assuming Earth-like greenhouse effects, was about 22 degrees Celsius, room temperature. But that assumed an Earth-like atmosphere, which this planet almost certainly doesn't have. Add more greenhouse gas and the planet gets hotter. Reduce the greenhouse effect and it gets colder. Without observation, without spectroscopy, we're essentially guessing. But there's something else about Kepler 22b that makes it different from Earth in a way that might matter even more than composition or atmosphere or temperature. Kepler 22 is an old star, about 7 billion years old. The Sun is only 4.6 billion years old. That means Kepler 22 has been stable, shining steadily, for 2.4 billion years longer than our Sun has. If life exists on Kepler 22b, it has had that extra 2.4 billion years to evolve. That's a 50% head start relative to the age of our star. Evolution on Earth took about 3.5 billion years to go from simple microbial life to complex thinking organisms. 50% more time than that. You could imagine what evolution might produce in that span. You could imagine ecosystems that are vastly more complex, more adapted, more mature than anything on Earth. Or, and this is the alternative that's almost as interesting, you could imagine that life hasn't emerged at all, despite billions of years of favourable conditions, which would suggest something fundamental about how rare life actually is, how unlikely it is that a planet like this ever spawns consciousness. But we can't know. We can't even begin to answer that question about Kepler 22b because we can't see it. We can see that it exists, yes. We can measure the shadow it casts when it crosses in front of its star. We can measure how long that shadow lasts and how much light gets blocked, and from that we can calculate its radius. We can search for the gravitational wobble in the star's motion and set upper limits on its mass. We can do all of that from 640 light-years away. But we cannot taste the air. We cannot see the colour of the ocean. We cannot send a probe there and get back images of what's really happening on the surface or at the bottom of the sea. This is the cruelty of the cosmos. The universe shows you a world that might harbour life, orbiting a star like your own, in conditions that seem almost hospitable, and then it puts 640 light-years of hostile vacuum between you and the answer. It dangles a question in front of you, a mystery that might be one of the most profound questions you could ask, and then it makes sure you can probably never solve it. That's the premise of Kepler 22b. That's what makes it tragic and fascinating in equal measure. You're looking at a world that exists, that's real, that might be alive with everything from microbial ecosystems to strange, evolved civilizations, and you're separated from it by a distance so large that the light that left that star when it began its journey toward Earth travelled for 640 years through empty space to reach your eyes. When that light arriving at Earth carries the image of this planet, the star itself might have changed. Stellar activity fluctuates. The planet's orbit might have shifted in ways you can't measure. anything could have happened in the 640 years since the light that paints this picture actually left that distant system. This is where we need to talk about what those 640 light years actually mean. It's a number that sounds manageable when you hear it. Thousands, hundreds of thousands. You can hold that in your head. But when you convert it into something more concrete, when you try to translate that distance into the time it would actually take to cross it, the number becomes something else. It becomes genuinely unsettling. So let's talk about those 640 light years. Let's put them in perspective. Because what we're about to reveal will change how you think about whether humans could ever reach a world like Kepler 22b, or whether the universe has made that permanently, physically impossible. Part 4. What 640 light years actually means. Let's talk about distance, because the number 640 light years doesn't mean anything to you yet. It shouldn't. Your brain didn't evolve to process it. So we're going to convert it into things you can hold in your mind, even if what you're holding is impossible. Start here. 640 light years equals roughly 6.05 quadrillion kilometers. That's the number 6 followed by 15 zeros. If you wrote out every kilometer between Earth and Kepler 22b, you would use more digits than grains of sand on every beach on Earth. But let me give you something more concrete. The distance from Earth to the Sun is about 150 million kilometers. Astronomers call this the astronomical unit, or AU. It's our yardstick. When we talk about the solar system, we measure in AUS because kilometers become meaningless noise. Kepler 22b is approximately 40.5 million times the Earth-Sun distance away. 40.5 million astronomical units. If the Sun and Earth are your nose and forehead, Kepler 22b is somewhere beyond the edge of the observable universe, measured in the scale of your face. Now, the weird part. The light we're seeing from Kepler 22b right now left that star not at the moment we took the photograph but 640 years ago. The Kepler Space Telescope captured photons that had been travelling through the vacuum for centuries before they arrived at our detector. Those photons left Kepler 22b in the year 1386. The 100 Years' War had just begun. The Black Death was about to sweep across Europe and kill a third of the continent. The Ming dynasty was 18 years old. The Aztecs hadn't even founded Tenochtitlan yet. It wouldn't happen for another century. Those photons crossed the galaxy while human history marched on below. They crossed while the Renaissance happened, while Columbus sailed, while the Industrial Revolution began and ended, while we split the atom and landed on the moon. And then, in 2011, they finally reached our little metal telescope above Earth's atmosphere, and we looked at them and called the thing they came from Earth 2.0, as if we had discovered something we could reach. We established in an earlier part that light travels at 300,000 kilometers per second, the speed limit of reality itself. Nothing can go faster. This is the speed that defines causality, the speed at which the universe enforces the rule that causes come before effects. Light is fast in the way that only massless particles can be, and light is unbearably, impossibly slow when you're trying to cross the galaxy. If we could send a signal to Kepler 22b right now, it would take 640 years to arrive. The people who received it would be reading a message sent by someone who's been dead for centuries. If they replied immediately, we would receive their response in the year 2666. That's how far away we're talking. That's 1 light year per year of travel time, at light speed, the speed nothing can achieve but light itself. Let's use Pluto as a reference point. Pluto is no longer a planet, but it's still a useful cosmic landmark. It orbits the Sun at about 39 astronomical units. It took Voyager 1 decades to reach it. Kepler 22b is approximately 1 billion times farther away than Pluto. 1 billion. If Pluto's in your backyard, Kepler 22b is so far away that the distance would bend around the curvature of Earth several hundred times and still not be close. Think back to a few videos ago when we established that light is agonizingly slow across cosmic distances. We talked about how even the fastest thing in the universe crawls when it has to traverse the void between stars. Now let's apply that concept to a specific destination. Imagine you send a message by laser beam from Earth to Kepler 22b right now. in this moment. That beam of light will arrive at its destination in the year 2666. Not a typo. 641 years from today. And if someone there, by some miraculous chance, received your message and sent a reply back at the speed of light, that response wouldn't reach Earth until the year 3306. A single round-trip conversation takes 1,280 years. That's longer than the entire history of the Renaissance, the Age of Exploration, the Industrial Revolution, and the modern technological era combined. A message exchange that spans longer than human civilization has existed in its current form. You might remember when we covered Voyager 1 and its measurements of the interstellar medium. We talked about the cosmic ray flux, the plasma hum, the wall of fire at the heliopause where the solar wind finally gives up its fight against the galaxy itself. That spacecraft has been travelling for nearly half a century, one of the fastest moving objects humanity has ever created, and it still hasn't left the sun's neighbourhood. We're talking about a region of space that would take it tens of thousands of years to escape. Voyager is currently about 235 billion miles from home. That sounds incomprehensibly far until you realise it's only a tiny fraction of the distance to Kepler, 22b. Our target star system sits approximately 40.5 million times farther away than the Earth is from the Sun. If Voyager maintained its current speed without ever slowing down, without any mechanical failures, if it could somehow escape the Sun's gravity and point toward Kepler 22b and keep going forever, it would take roughly 14 million years to get there. 14 million? That's before your species learned to farm. That's longer ago than the earliest hominids walked upright on the African savanna. That's longer than some estimate for the entire existence of modern humans on this planet. The distance doesn't just challenge us technologically, it challenges us psychologically. It forces us to confront the fundamental separation between our world and theirs. We exist in a solar system that our fastest spacecraft will never truly leave in any meaningful time frame. The stars hang above us every night, and they've done so for all of recorded history, for all of human consciousness, and they remain as distant as ever. Kepler, 22b, isn't just far away. It's indifferent to human ambition. It orbits a star that we can only perceive as a point of light, a mathematical abstraction, a place that exists primarily in data and simulation, rather than in any tangible reality we can reach or touch or even meaningfully comprehend in human terms. Here's the measurement that will actually break something in your understanding. Voyager 1 has been travelling through space for over 50 years. It's been pushed faster than any human-made object, cruising at about 165 astronomical units per decade. Voyager 1, the fastest thing we've ever created, moving away from Earth at 17 kilometers per second, would take 18,000 years to cross a single light year. 1 light year. 640 light years to Kepler. 22b means 11.2 million years at Voyager's speed. Homo sapiens, you, me, everyone who has ever felt pain or love or curiosity, has existed for about 300,000 years. Voyager would need 40 times the entirety of human existence to reach another star. And Kepler 22b isn't another star, it's a planet orbiting another star. The Parker Solar Probe currently holds the record for the fastest human-made object. It travels at 692,000 kilometers per hour. That sounds fast. It's the speed that will incinerate it from friction with the solar wind, and it's 0.064% the speed of light. At that velocity, the time to reach Kepler 22b would be 9.4 billion years. The Sun will have died by then. It will have expanded, consumed Earth, and cooled to a white dwarf. The Parker Solar Probe, travelling at speeds that would take you across Earth's circumference in 1 minute, would be travelling for longer than the Sun has existed. The star will grow old and die and cool while we're still, comparatively, barely moving. This is the wall. This is the thing that stops every space program, every theory, every dream. It's not a wall made of material. You could punch through a wall of steel. This wall is made of the structure of reality itself. It is physics saying, no further. You're bound to your star, and all stars are bound to their distance from all other stars, and these distances are measured in the speed of a light, which is the fastest anything can go. And we have done the math, and the math does not have a loophole. Yet we tried anyway. Humanity has always looked up and refused to accept limits. We imagined ways to go faster. We drew up blueprints for ships powered by nuclear explosions. We calculated the yield required if we bent space-time itself. We dreamed of antimatter engines and lasers and exotic matter that doesn't exist. The question we need to answer is not whether we could theoretically leave the solar system, we've already done that. The question is whether any of these engineered dreams could actually shorten the journey to Kepler 22b into something measured in centuries rather than millions of years. And if so, what would it cost? Part 5. The engines we have dreamed of. Let's start with the ones we've actually designed on paper, in detail, with physics we know works or could work. There's a proposal called Breakthrough Starshot, funded by Yuri Milner and supported by Stephen Hawking before he died. The idea is to build a phased laser array that outputs 100 gigawatts of light. That's roughly 10 times the output of a large nuclear power plant, all focused in one direction. At the focal point, you place a gram-scale nanocraft. The laser pushes it to between 15 and 20% the speed of light in about 10 minutes. 10,000 g-forces of acceleration. The human body can sustain about 9 g-forces before losing consciousness. At 10,000 g-forces, your blood would weigh as much as a truck. Your organs would turn into liquid. But there are no humans aboard. The spacecraft is the size of a postage stamp and weighs about as much as a thumbtack. The laser doesn't need to be turned off after 10 minutes, so the acceleration continues. Within a short time, the nanocraft is cruising at 1/5 the speed of light. For Kepler 22b at 20% of light speed, the journey takes 3,200 years. The nanocraft would need to coast for all of it. There's no deceleration mechanism. It would arrive at Kepler 22b and pass through the system in minutes, cameras recording everything, data transmitted back toward Earth. If everything goes right, that data reaches us after another 640 years. So we would get a picture of Kepler 22b from the year 5532. We would have waited 9,500 years for a photograph. The civilization that launched the mission would be extinct. The language used to name it would be dead. But we would finally know what's actually there. Then there's Project Orion, developed in the 1950s and 60s by physicists including Freeman Dyson. The idea was strikingly simple and utterly insane. You build a large, strong plate attached to the spacecraft by springs. You stand a small nuclear bomb on the plate and detonate it. The explosion pushes the plate, which pushes the springs, which accelerates the spacecraft. Then you do it again, and again, hundreds of times. You're riding a series of controlled nuclear explosions across the solar system. With this method, Project Orion calculations suggested a spacecraft could reach speeds of 9 to 11% the speed of light. The journey to Kepler 22b would take 6,400 to 7,100 years. But that assumes you use half your fuel to accelerate and half to decelerate, so you could actually slow down when you arrive. With deceleration, you're looking at roughly 9,000 years. It was never built. The Limited Test Ban Treaty of 1963 banned nuclear explosions in the atmosphere and in space. Orion was shelved, and humanity moved on to other fantasies. Project Daedalus came next, designed by the British Interplanetary Society between 1973 and 1978. The engineers involved, particularly Alan Bond, designed a fusion rocket using a reaction between deuterium and helium-3. The ship would be enormous, 54,000 tons at launch. 93% of that would be fuel. 250 fusion pellets would be detonated per second, each one providing a tiny burst of thrust. The ship would accelerate for about 4.5 years, reaching 12% the speed of light. The journey to Kepler 22b would take 5,333 years. The payload, the part that wasn't fuel, would be 500 tons. About 1% of the spacecraft's total mass would actually be cargo. Everything else would be consumed, burning itself across the stars. The calculations were sound. Daedalus has never been built. The technology doesn't exist. We don't have engines powerful enough or fuel efficient enough. We don't have a reason to build them. Every single one of these approaches hits the same wall. You can accelerate faster with nuclear bombs than with any conventional rocket. You can be clever and use fusion instead. But you still need staggering amounts of fuel, and you still need years to accelerate, and you still end up at only a fraction of light speed, and the journey still takes thousands of years. The fundamental problem is energy. Moving mass across space requires energy. Moving large mass very fast requires enormous energy. Moving very large mass very fast across 640 light-years requires energy that no single nation has ever produced. Then there's antimatter. This one is seductive because the physics is simple. Matter and antimatter annihilate each other in a burst of pure energy. Einstein's famous equation, E equals mc squared, describes the conversion. 1 gram of matter meeting 1 gram of antimatter releases the energy equivalent of 43 kilotons of TNT. That's about 3 times the yield of the bomb dropped on Hiroshima. A spaceship powered by antimatter annihilation could reach 50% the speed of light with a reasonable fuel ratio. At 50% light speed, the journey to Kepler 22b takes 1,280 years. Still a very long time, but measured in centuries rather than millions of years. The problem is production. CERN, the European Organization for Nuclear Research, with its massive particle accelerator and billions of dollars in funding, produces about 10 nanograms of antimatter per year. 10 nanograms. 1 gram would require 100 billion years of CERN's production. If we could somehow scale up production and do it perfectly efficiently, it would cost about $62 billion per microgram of antimatter. The total cost to produce 1 gram would exceed the economic output of human civilization. And that's just 1 gram. You would need tons of antimatter for an interstellar spacecraft. The containment problem is equally nightmarish. Antimatter has to be kept in a magnetic bottle, suspended in a vacuum, never touching normal matter, or the entire payload annihilates instantly. 1 breach, 1 power failure, 1 collision with a micrometeorite, and your spaceship becomes a nuclear bomb. Then there's the mathematical dream that physicists have been chasing since Einstein, the warp drive. In 1994, a physicist named Miguel Alcubierre published a paper describing a solution to Einstein's field equations that would allow a spacecraft to distort spacetime itself. The idea is simple in concept. Space in front of the ship contracts, space behind it expands, and the ship rides the wave like a surfer. Locally, you're not travelling faster than light. You're just riding space-time itself, which can expand and contract as fast as it wants. You could, in theory, reach Kepler 22b in days. The problem is the energy required. The original Alcubierre calculation said you would need the energy output of the entire observable universe. Not the energy of the sun, not the energy of all stars. The energy of every star in every galaxy in every direction to the edge of what we can see. Recent papers from 2020 and 2025 have brought that down to about 4.9 million joules. That sounds reasonable. It's the energy in a ton of TNT. But there's a catch. The energy has to be negative. You need exotic matter with negative energy density, negative mass, negative gravity. Nothing like this has ever been observed. It may not exist. It may violate causality. It may be impossible. Let's step back and talk about energy requirements in general terms. A 50,000-ton spacecraft accelerating to 10% the speed of light requires about 3.8 times the total energy output of human civilization. Everything we make. Every power plant, every solar panel, every hydroelectric dam, every bit of energy we produce in an entire year, you would need to take more than 3 times that and convert it into acceleration. To reach 50% light speed, you would need 1,876 times annual global energy production. To reach 90% light speed, You would need 33,500 times global energy production. And that's just acceleration. You need to decelerate at the end, or you'll pass right through the system at destructive speed. Deceleration doubles the energy requirement. There is no shortcut here. There is no clever engineering that gets around this. Physics is very clear. Moving matter across space costs energy, and the faster you want to go and the more mass you want to move, the more energy you need. The equation doesn't have a loophole, so let's imagine we solve this impossible problem. Let's imagine we invent fusion power that's so efficient it breaks the conservation of energy slightly, and we become a Type 2 civilization that harvests the power of our sun and builds an antimatter engine that somehow doesn't blow up. We've built a spacecraft with the best propulsion humanity could ever dream of. It can reach 12% the speed of light. It's ready to launch toward Kepler 22b. The journey will take 5,333 years. 10 generations will be born and die and be forgotten before arrival. But there's a worse problem lurking in that 5,000-year journey. We've been talking about space as if it's empty. We've been drawing our diagrams with a spacecraft crossing a blank void. The space between stars is not empty. It's not even mostly empty. It's full of things that want to kill you. And at the speeds we've been discussing, 10, 20, 50% of light speed, every single thing in space becomes a weapon. Part 6. Time dilation will not save you. There's a beautiful idea in special relativity, Einstein's theory of how time and space are woven together. The idea is that time moves differently depending on how fast you're travelling relative to an observer. If you move very fast, time slows down for you. If you could travel at 99.9% the speed of light, you could age 1 year while centuries passed on Earth. You could reach distant stars in your subjective time, while the civilization that launched you fell into history. Time dilation is supposed to be the ace up our sleeve. It's the thing that makes interstellar travel almost possible. Almost. The math for time dilation uses something called the Lorentz factor. The faster you go relative to the speed of light, the more the factor changes and the slower time moves for you. At 10% the speed of light, the Lorentz factor is 1.005. That means for every year that passes on Earth, you experience about 0.995 years. You save 30 days out of 365. Out of a 6,400-year journey, time dilation saves you 30 years. 30 years. After 5,000 years of travel, you arrive 6,000 years after launch, having aged barely any less than people on Earth. Time dilation is negligible at 10% light speed. At 50% light speed, the Lorentz factor climbs to 1.15. Your time relative to Earth's time is now about 0.86. You're aging about 14% slower. The journey to Kepler 22b is 1,280 years in Earth time, but you experience only about 1,109 years. You save about 171 years. That's significant. You miss about 6 generations of change on Earth, but you're still aboard a spacecraft for over a millennium. You're still a prisoner in a metal tube. You're still dead before the journey ends, and your children are dead, and your grandchildren are dead. You're still travelling for centuries regardless of time's local trickery. To make time dilation actually matter, you need to reach velocities above 95% the speed of light. At 95% c, the Lorentz factor jumps to 3.2. Time aboard the ship runs at about 30% the speed of time on Earth. A 5,300-year journey is crushed down to about 1,300 years shipboard time. You've saved 4,000 years. That's real. But the energy required to accelerate a 50,000-ton spacecraft to 95% light speed exceeds 33,000 times the annual energy output of all of human civilization. You would need to harness the output of the sun for roughly 1,000 years just to build up enough energy to accelerate a single spacecraft. And that energy budget doesn't include deceleration, or any margin for error, or the weight of fuel required to accomplish any of this. Time dilation was supposed to be the solution that made the galaxy reachable. Instead, what we find is that the energy required to make time dilation matter is so staggering that we're back to the original problem. The journey takes thousands of years no matter what trick we try to apply. Time dilation doesn't save you. It can't. The universe doesn't allow escape from the basic constraint that moving mass across space requires energy, and there's only so much energy available. Even at 90% the speed of light, you're still looking at 310 years aboard that ship. 310 years. That's 10 generations born in the dark, children who will never see Earth, who will grow up in corridors lit by artificial stars, who will inherit a journey they didn't choose. Their great-great-grandparents boarded the vessel. Their great-grandparents were born during acceleration. Their grandparents grew up in the vast emptiness between stars. Their parents knew only the hum of the engines and the particular shade of grey in their cabin walls. And then they arrive, and they step out onto a world their ancestors dreamed about, and they're standing on alien soil, while everyone they ever heard about in stories, everyone on Earth, everyone in the entire solar system, has been dead for 3 centuries. You can talk about time dilation as an elegant solution, a mathematical miracle, but sit with that for a moment. Sit with what it means to be born into a metal tube and never leave it, to live your entire life watching the same 1,000 faces age around you, to know that your childhood friends will be old and grey before you reach the midpoint of the journey. The ship becomes a world unto itself, a closed society with its own language evolving, its own customs drifting further from Earth with each passing decade. The people on the ship age slowly relative to Earth, but they still age. They still feel time. They still experience the weight of waiting. This is where people usually imagine time dilation as a cheat code, a clever exploit in the rules of physics that lets us slip through the cosmos faster than light itself would allow. But the universe doesn't offer shortcuts. It only offers terrible trades. Every increment of speed demands exponentially more energy. The jump from 80% to 85% light speed cost you thousands of times more fuel than the jump from 50 to 55%. The jump from 90 to 95% is almost incomprehensible. The closer you get to the speed of light, the more the universe tightens its grip. You're climbing an infinite staircase where each step gets steeper than the last, and the air gets thinner, and you're burning fuel just to go from one step to the next. The mathematical cruelty is almost beautiful in its precision. At 50% the speed of light, your ship's clock runs at 87% the speed of Earth's clock. At 90%, it runs at 44%. You'd think that doubling your speed would halve the time, but that's not how relativity works. The benefits get smaller and smaller while the costs grow without limit. You're reaching for an asymptote, a mathematical horizon you can never quite touch. For every year you save with additional speed, you're spending decades worth of resources. The equation doesn't balance. It never balances. So you're floating in this bubble of slowed time, this pocket of relativity that moves through space like a stone dropping through still water. And outside your windows the stars are shifting. Not quickly. It takes weeks for a star to noticeably move against the background. It takes years for the familiar constellations to start looking strange. But you watch it happen. You have decades and centuries to watch it happen. You watch the Orion that you learned about in school gradually twist into a shape your children won't recognize. The pole star drifts. The zodiac slowly rewrites itself. And you're aging at a normal human pace while all of that happens, feeling every day of it, and the radio signals from Earth are growing older and older. The messages that come take longer to arrive. A message sent when you left Earth takes centuries to reach you, and by the time you receive it, the person who sent it is long dead, and their great-great-grandchildren might be dead too. You're separated from Earth not by distance, but by time itself, by a gap that grows with every year of your journey. The loneliness isn't metaphorical, it's mathematical, it's written into the physics. There's another problem with time dilation that nobody really wants to talk about. If you leave Earth in the year 2026 and you travel for 5,000 years at relativistic speeds, while only aging 1,000 years, you arrive in the year 7026. The civilization that built your spacecraft has been extinct for 4,000 years. The language they spoke has been dead longer than Latin. If anyone is there to receive your message, they won't speak your language. They won't use the same measurements. They won't value the same things. They might be so alien in their culture and technology that they look at your spacecraft the way we look at a Sumerian clay tablet, an incomprehensible artifact from an incomprehensible time. You've become a temporal refugee. You've launched from a world and arrived at a destination so far in the future that home is effectively destroyed. You're not an explorer anymore. You're a ghost. Your people have evolved or been replaced or forgotten you entirely. The relativity that was supposed to make long voyages survivable actually guarantees that you'll arrive as a relic from the distant past. The hard truth is this: time dilation will not save you. Nothing will save you. There is no engine, no trick of physics, no clever engineering that gets around the basic constraint. 640 light-years is too far. The physics doesn't bend. The equations don't have hidden solutions. Every calculation points to the same conclusion. If you want to leave the solar system and travel to another star, you will spend centuries aboard a spacecraft. You will be born and die and be forgotten aboard a spacecraft. Your children will know the stars only as a line of light outside a window. Your descendants will think of you as ancient history. And when you finally arrive, if you finally arrive, the world you left behind will have transformed beyond recognition. You will never see it again. Your home will be lost to you, and Kepler 22b, when you reach it after 5,000 years of travel, will not welcome you. It will be just as unreachable as it is today. Part 7. The Invisible Storm. You've been assuming that space is empty, that once you leave Earth's atmosphere you're in a vacuum, nothing between you and where you're going. That assumption keeps most of us sane. It's also wrong. The space between stars isn't a void, it's a populated place, and everything living in it is trying to kill you. Start with the basics. The interstellar medium, the gas and dust that fills the galaxy, is made mostly of hydrogen. Molecular hydrogen, atomic hydrogen, scattered helium, trace amounts of heavier elements forged in stellar furnaces and scattered into the dark when those stars died. If you measured it in Earth's atmosphere, this would be an incomprehensibly thin gas, about 0.1 atoms per cubic centimetre. For comparison, Earth's atmosphere at sea level is around 10 to the 19th atoms per cubic centimetre. The interstellar medium is 14 orders of magnitude sparser. If you tried to breathe it, you wouldn't even notice anything entering your lungs. It's that thin. The silence of space, that detail people get right, comes from this emptiness. Sound needs molecules to travel through. Out there are barely any. A sonic boom requires collision. In the interstellar medium, collisions are so rare that sound is essentially impossible. There is genuinely quiet out there. But thin doesn't mean harmless. The problem isn't the gas itself, it's what's riding on it. Cosmic rays. These are the real inhabitants of interstellar space. Particles accelerated to nearly the speed of light by the deaths of stars, by the collision of shock waves across light years, by processes we still don't fully understand. Mostly protons, fast protons, carrying the kinetic energy of stellar violence, but also heavier particles, carbon nuclei, oxygen nuclei, and the worst ones, the heavy ions, ion nuclei moving at 99.9% the speed of light, carrying energy that conventional physics barely captures. Here's what makes cosmic rays particularly relevant to your journey. Earth's magnetic field stops most of them. The heliosphere, the bubble of solar wind and magnetic field that the sun extends around itself, blocks something like 50 to 70% of the cosmic rays that would otherwise saturate the inner solar system. It's a shield you've been living inside your entire life without knowing it existed. It's kept you alive in a way most people never realize. Leave that shield behind, and the numbers change. The Voyager 1 spacecraft crossed the heliopause, that boundary between the sun's magnetic protection and true interstellar space, on August 25, 2012. Voyager had been flying outward for 35 years at that point. When it crossed that boundary, its cosmic ray sensors experienced a sudden jump in galactic cosmic ray flux. The instruments detected an increase of 30 to 50% almost instantaneously. The spacecraft's plasma wave sensors began picking up a hum, a radio noise from the electron-dense interstellar medium outside the heliosphere that Voyager had never heard before. For the first time in its mission, Voyager was listening to the sound of genuine interstellar space, and that sound was a constant hiss, a static wall that didn't quiet. Now imagine flying through that for 5,000 years. The radiation problem becomes exponentially worse if you're going fast. Here's why. If you're travelling at 30% the speed of light, one of the faster scenarios we've discussed, the hydrogen you're flying through isn't stationary relative to your ship. From the frame of reference of your vessel, that hydrogen is coming at you at 30% light speed. That makes it a cosmic ray. You've essentially created your own radiation field by virtue of moving too quickly through space. The flux of hydrogen ions hitting your hull at 30% C exceeds 3 billion atoms per square centimetre per second. The equivalent energy is catastrophic. There's a term for this: relativistic hydrogen bombardment. Unshielded, electronics begin failing within minutes. The biological equivalent would be exposure to the radiation produced by 20 nuclear reactors, all of them going critical, all of them aimed at your hull. The shielding requirements are staggering. At 30% light speed, you need roughly 2 centimeters of titanium to provide meaningful protection. At 80% light speed, a speed some theoretical propulsion systems hint at, you need several meters of additional shielding. That's not extra plating. That's a barrier meters thick. You're now hauling that mass for 5,000 years. Your fuel requirements just went from impossible to even more impossible. Then there are the high atomic number ions, the HZE particles. These are heavy nuclei accelerated close to light speed. Iron nuclei are the worst. An iron nucleus moving at nearly light speed doesn't care about conventional shielding. It passes through armor like a bullet through paper. It doesn't just hit your electronics and your hull. It passes through the entire ship. It passes through the crew. One of those particles striking at the right angle might pass through a human brain. The damage it causes isn't instant. The ion creates a trail of ionization, excitation, and injury along its path. The cell death occurs downstream from the impact, in a sphere of damage that can be millimeters in diameter. For a single particle, it's usually survivable. The crew member might not even notice. But there are billions of these collisions happening every second once you leave Earth's magnetic protection. Reference the research from Mars radiation studies conducted by NASA. The surface of Mars receives about 0.64 millisieverts of radiation per day from cosmic ray sources, roughly 200 times higher than Earth's surface. Mars missions, lasting around 2.7 years, give astronauts a radiation dose on the order of 300 to 600 millisieverts total, depending on solar activity. This is a concerning but manageable level for a mission that's short, and NASA monitors it carefully. The space station in low Earth orbit, still protected somewhat by Earth's magnetosphere, gives astronauts roughly 50 millisieverts per year. Now imagine flying through unshielded interstellar space for 5,000 years. The accumulated radiation dose would be staggering. The crew wouldn't just get sick, they'd accumulate cellular damage at a rate that would cause accelerated aging, increased cancer risk, organ failure, and, most importantly, genetic damage. Mutations would accumulate in the DNA of each person and would be passed to their children. Some mutations are neutral, some are beneficial, most are harmful. Over dozens of generations in a high radiation environment, the mutation load, the total number of harmful genetic changes, would accumulate faster than evolution could weed them out. That's a problem for a closed population of 500 people with nowhere to go and nothing to do but keep flying forward. The dust is another hazard. The interstellar medium carries ancient dust, particles of silicate and carbon from the deaths of stars that ended 1 billion years ago. These are tiny, maybe micrometers across, scattered through space so thinly that your ship might go hours without a collision. But when one hits, at the speeds you're travelling, physics delivers a moment of violence that shouldn't fit into something so small. A dust grain 100 micrometers in diameter, a grain you could barely see without a microscope, travelling at 10% light speed strikes your ship. The kinetic energy released is equivalent to a 100-ton object hitting you at highway speed. That's not a scratch. That's an impact crater. Now speed it up. At 30% light speed, that same grain releases energy equivalent to kilotons of TNT. Kilotons. A single dust grain becomes a small bomb. We know there are dust clouds out there. We can map them with infrared telescopes. What we don't know is their exact density along any particular path through interstellar space. It's a poorly characterized hazard. Your route to Kepler 22b might take you through a relatively clean corridor, or it might take you through regions of elevated dust density. You won't know until you're in the midst of it, and by then, your hull is already taking impacts that could penetrate kilometers of steel. So the ship moves through a radiative landscape, that steady drizzle of high-energy particles, those occasional dust grain bullets, that constant hum of the interstellar medium pressing against your shields. The engines maintain their rhythm. The radiation counters tick steadily, endlessly, counting the particles and the damage. The hull develops tiny crater marks and degradation in materials that engineers will try to repair but can never fully control. Shielding ages, materials become brittle. The ship, built to last 5,000 years, is being slowly corroded by the very medium it's travelling through. And that's just what's happening on the outside. The real horror isn't the radiation coming from space. The real horror is what happens to the people inside as that radiation passes through their bodies, day after day, year after year, generation after generation, and nobody is going home. Nobody's going to extract the crew and place them in a hospital on Earth. There is no rescue. There is no evacuation. There's only forward, always forward, into that hum and that hiss and that invisible bombardment that you can't see or hear, but is always there. This is the invisible storm, not a hurricane, not a thing you can fight or navigate around. Just the steady, relentless violence of the universe, applied in small increments across the scale of human lifetimes and longer. The kind of danger that kills slowly, secretly, in ways you don't understand until it's already written into your genes. But the outside hazards, terrible as they are just the beginning. Part 8. What space does to a body. Imagine waking up one morning and being unable to stand. Not because you're tired, not because you're injured, but because your bones have lost a quarter of their density, your muscles have withered to half their strength, and your cardiovascular system has downsized so dramatically that trying to support your own weight would cause you to black out. This isn't a disease. This is what happens to astronauts in microgravity. The International Space Station orbits Earth once every 90 minutes. Gravity still pulls on it. Gravity pulls on everything, but the station and its crew are falling at the same rate. They're in free fall, which feels like weightlessness. The Earth is pulling on them with the same force as it pulls on you right now, but because they're falling, they don't feel it. In this state, in genuine weightlessness, the human body begins to fall apart. Bone loss begins immediately. Astronauts lose bone density at a rate of 1 to 2% per month in microgravity. After 6 months on the space station, they've lost the amount of bone density that a sedentary elderly person loses in a year on Earth. After a year, they've developed osteoporosis equivalent to someone in their 60s or 70s. The loss isn't uniform. It's worst in the weight-bearing bones, the femur, the tibia, the pelvis, the bones that evolved over millions of years to support the weight of a human body against Earth's gravity. Without that gravity, they stop rebuilding themselves. Astronauts on the space station fight this by exercising aggressively. 2 hours per day, minimum, on treadmills and resistance equipment, trying to maintain the mechanical stress on bones that signals them to stay strong. It slows the bone loss. It doesn't stop it. An ISS crew member comes home and begins a careful rehabilitation to rebuild their bones. Physical therapy for weeks. It's recoverable, but it's an effort. Now imagine a crew that never comes home. On a generation ship bound for Kepler 22b, the crew lives in an artificially created environment. The ship probably rotates to simulate gravity through centrifugal force, but let's be realistic. Rotating habitats are engineering challenges we've never solved. We've never built one. We've never tested one for 5,000 years. Many designs for generation ships propose microgravity environments, smaller ships, easier to maintain, easier to shield from radiation. In these designs, crews live without gravity. Muscle loss happens faster than bone loss. In the first month of weightlessness, astronauts lose about 20% of their muscle mass. Strength declines even faster, 30% strength loss in the same month. The body, operating on an evolutionary assumption that if you're not using your muscles to hold yourself up, you don't need them, begins cannibalizing them. It's not cruelty, it's efficiency. Muscle tissue is metabolically expensive. If gravity isn't forcing your muscles to work, your body says, why waste calories maintaining them? The muscle fibers begin to break down, converted back into amino acids and recycled for other uses. A crew member gets used to this. They adapt. Their cardiovascular system shrinks. Their muscle mass stabilizes at a new, lower level. They live their entire lives in microgravity, moving with practiced ease through their environment, exercising regularly, adapting to the physics of their world. Then, their children are born. This is where the generations problem becomes genuinely terrifying. A child born on a spacecraft in microgravity never experiences gravitational loading. Their bones don't develop the same density as bones that grew under stress. Their muscles develop differently. The neural signals that guide muscle growth, the mechanical feedback that tells bones how strong to become, all of these are calibrated to a world of zero gravity. There's another system affected, the vestibular system, the inner ear apparatus that tells your brain which way is up. It develops to match the environment. Children born in microgravity calibrate their vestibular systems to zero gravity. Their brains learn to interpret space and motion in the absence of a gravitational reference frame. When they grow up, they move through the ship with perfect ease. They've never known anything else. The heart adapts first and not for the better. In zero gravity, the human cardiovascular system begins a slow reorganization. Your heart, that muscular fist that has beaten steadily since before you were born, actually shrinks. It becomes more spherical, less efficient, because it no longer needs to fight gravity's constant pull. The chambers round out, the muscle weakens. Astronauts returning from the International Space Station show measurable decreases in cardiac output, and they were only up there for 6 months. Now imagine what happens over 200 years. The heart of a child born in this environment would be fundamentally different, smaller, rounder, adapted perfectly for a world where pumping against gravity has become unnecessary. But there is a hidden cost. As the heart weakens, blood pools differently throughout the body. It redistributes upward, toward the head and chest. Fluid shifts, intracranial pressure begins to increase. The optic nerves, those delicate cables that carry vision to the brain, come under pressure. Astronauts on the ISS have reported something unsettling. Their vision changes, not temporarily, permanently. After just 6 months in space, some develop what doctors call spaceflight-associated neuroocular syndrome. The pressure behind the eyes increases so much that it actually reshapes the eyeball, flattens it slightly. Vision blurs. The optic disc swells. For a crew travelling 200 years, with children born and raised in this environment, the cumulative effect is almost impossible to predict. What does it mean for a human being who has never experienced the pressure that shapes a typical Earth eye? What does a cosmos look like through eyes that were literally formed in weightlessness? And then there is the immune system, perhaps the most fragile system of all. Microgravity weakens it. This is not a minor change. Exposure to the stress of weightlessness, the constant background stress on every cell, causes immune function to decline. T cells, those sentinel cells that identify and destroy invaders, become less responsive. Their ability to mount a defense drops measurably. Worse, something else happens that seems almost paradoxical. Dormant viruses wake up. Herpes simplex, the virus that most humans carry silently in their nerve cells, reactivates in space. It emerges as though gravity was somehow holding it in check. Varicella zoster, the chickenpox virus hiding in the bodies of vaccinated crew members, can reactivate as shingles. Astronauts on short missions have experienced this. But a short mission is one person, isolated in a space station, careful and quarantined. This is different. This is 500 people. 500 people in a sealed ship travelling through darkness for generations. 500 people whose immune systems are collectively weakening, whose dormant infections are surfacing, whose ability to fight new pathogens is declining with each passing year. In a closed population with no option to leave, no way to quarantine beyond a few small rooms, disease becomes not a possibility, but a statistical inevitability. A virus that would burn through the crew and retreat on Earth, contained by vaccination and distance and open air, would find 500 vulnerable hosts in a metal tube. It would spread from person to person, from generation to generation, adapting, mutating, becoming embedded in the community. This is the kind of pressure, not the gentle pressure of weightlessness, but the biological pressure of isolation that changes a species. And yet in the nursery of this ship a child floats. She was born here. She has never known anything but this. She reaches for a toy drifting beside her, and it comes to her. No effort, no falling, no resistance. She pulls herself along the wall by her fingertips and moves as gracefully as a dancer, because in this environment, everyone is a dancer. The older crew tell stories about weight. They describe it in ways that sound like mythology. They speak of a force that pressed down on you always, that made things fall, that required you to strain against an invisible hand every moment of your waking life. To this child, it sounds like a fairy tale. Gravity, they call it. The weight of worlds. She has accessed the archived files, seen videos of people on Earth moving stiffly, slowly, every gesture weighed down. She understands it intellectually as one might understand the properties of an element on the periodic table, but she has never felt it. She will never feel it. Everything she knows of motion and balance and how her own body moves through space comes from this flotation, this effortless gliding. When the original crew spoke of gravity as normal, she could not truly grasp it. Normal is whatever you're born into. For her, weightlessness is the ground beneath her feet. Everything else is alien. Now imagine, after 200 generations, after 5,000 years, after travelling 640 light years, the ship arrives at Kepler 22b. The planet's gravity is 1.3 times Earth's gravity. Kepler 22b is larger than Earth, and based on what we know of its density, its surface gravity is stronger than anything the crew has experienced. A crew member stepping out onto that world would feel immediately as if they weighed more. Their feet would press harder into the ground. Gravity would pull at them with a force they've never adapted to. The descendants who arrive after 200 generations have never felt gravity stronger than 0. Their bones are fragile. Their muscles are weak. Their vestibular systems are calibrated to weightlessness. If they tried to stand on Kepler 22b's surface, their legs would buckle. Their cardiovascular systems would struggle to pump blood against the stronger gravity. Vision would swim. Some might black out from the effort. They are the wrong bodies for the world they're trying to inhabit. There are potential solutions. A rotating section of the ship could provide artificial gravity for later generations, allowing them to adapt before arrival. But rotating habitats, as I mentioned, are engineering challenges we haven't solved. They're also heavy. They complicate ship design. Many proposals skip them. The radiation adds another layer of horror to this biological transformation. Over 200 generations, the crew is accumulating mutations. Not the dramatic kind that happens in science fiction, not sudden, visible mutations that make people into X-Men. The kind that happen in reality, small errors in DNA replication, accumulations of damage that manifest across generations. radiation exposure in ancestors increases the mutation load in descendants. In a small population, 500 people, maybe 1,000 if the ship is large, there's no genetic escape. Evolution works by selecting for beneficial traits and against harmful ones. But in a small population, rare harmful mutations can spread by chance. The population becomes less genetically robust. Children born later in the journey are statistically more likely to have health problems than children born early. Life expectancy declines across generations. Infertility increases. Miscarriages become more common. Birth defects become more frequent. The population that arrives at Kepler 22b is smaller, frailer, and genetically less diverse than the population that left Earth. Some geneticists argue that over 200 generations in a high radiation environment, the accumulated mutation load could make the arriving crew distinctly different genetically from the humans who left Earth. They might not be different enough to be considered a different species. They'd still be capable of reproducing with Earth humans, potentially, but they'd carry a genetic burden, a load of accumulated errors that would make them more prone to disease, faster aging, reduced fertility. The cruelest irony is this. The ship's trajectory and fuel calculations were designed for a specific destination mass and gravity. Kepler 22b, likely a mini-Neptune with an ocean surface and higher gravity than Earth, might not actually be survivable for a crew that's adapted to microgravity. The world you're trying to reach might kill your descendants simply because they're not physically suited for it anymore. But we've been focusing on the body. The mind is a different problem entirely. Part 9. The Loneliest Journey Ever Taken. The Voyager spacecraft, launched in 1977, has been transmitting data back to Earth for nearly 50 years. The signal takes about 20 hours to reach us, travelling at light speed across the solar system. It's the longest communication delay we routinely tolerate. Ground control at NASA's Deep Space Network receives the signal, analyses it, decides on commands if needed, and transmits instructions back. Even with the round-trip light delay of roughly 40 hours, the conversation between mission control and the spacecraft is still possible. It's slow, but it's real. Now imagine multiplying that delay by a factor of 10,000. A message from Earth to a spacecraft travelling toward Kepler 22b takes 640 years to arrive. The spacecraft receives it, processes it, and sends a response. That response takes another 640 years to reach Earth. The round-trip communication time is 1,280 years. This means, if mission control at NASA, assuming NASA still exists in its current form, transmitted a message to your spacecraft at the moment it launched, that message wouldn't arrive at the ship until the crew had travelled more than half the journey. The reply wouldn't reach Earth until 2,500 years had passed. In practical terms, there is no mission control. There is no conversation. There is no possible rescue. There is no evacuation. When the spacecraft launches, it severs its connection to Earth permanently. Everything that happens, every decision, every crisis, every catastrophe, must be handled by the 500 people aboard the ship, alone. The psychological implications are staggering. Let's establish a baseline. NASA and the European Space Agency have conducted extensive studies on isolation and confinement. The most relevant is probably Mars 500, a Russian study that confined 6 volunteer crew members to a sealed environment for 520 days, roughly 17 months, to simulate the isolation of a Mars mission. During that study, researchers measured depression using the Beck Depression Inventory, tracked interpersonal conflicts, monitored sleep disturbances, and observed psychological dynamics. The results are telling. Even in a 17-month mission, depression scores increased measurably in the third quarter, the point where crew members realised they were past the halfway mark but still far from home. Social conflicts between crew members increased. Conflicts with mission control increased. The crew's patience with communication delays shortened. There were tensions, arguments, moments where the confined space and the awareness of complete isolation began to wear on the psychological resilience of the participants. That study lasted about a year and a half. Now multiply it by 3,000 times. The first crew members who board the spacecraft are volunteers. They know what they're signing up for as much as anyone can. They're trained. They're psychologically screened. They're selected for their ability to handle isolation, their stability, their capacity to work in teams. They're the best version of who we can send, but they're human, and they're committing to 5,000 years of isolation. The second generation is born aboard the ship. They're also volunteers, technically. Volunteers in the sense that their parents chose to have children knowing those children would spend their entire lives in a spacecraft. That's a choice the parents made for them. The third generation grows up surrounded by metal walls. They've never felt rain. They've never seen an ocean or a forest or a sunset. They've never been outside. Earth is something their grandmother told them about. A story, perhaps a half-understood mythology. The destination, Kepler 22b, is a promise their children will work toward, but they'll never see it. By the 10th generation, we're talking about 300 years of continuous isolation. Humans born in the 23rd century, living in a metal tube in the middle of space, with only the vaguest understanding of where they came from or where they're going. By the 50th generation, we're talking about 1,500 years of isolation. The crew members at that point have less genetic connection to the original Earth population than a modern human has to humans from the Bronze Age. The mythology starts replacing the history. Earth becomes something half-legendary. Kepler 22b becomes a promised land that the crew is travelling toward, not for themselves, but for descendants 1,000 years in the future whom they'll never meet. The mission becomes religious. It becomes dogmatic. The ship's path is sacred. The mission is a pilgrimage. And that's when the problems really begin. Consider what happens to a story when it's told and retold across 200 generations. The crew members who launched from Earth carried with them a clear scientific mission. They knew why they were travelling. They understood the physics, the biology, the engineering that kept them alive. But language changes. Words shift their meanings. A technical term becomes slang, then becomes poetry, then becomes mythology. After 50 generations, the word for the reactor might have transformed so completely that no one remembers it ever meant anything literal. The original reason for the journey, to find a habitable world, to establish a colony, to expand human civilization, begins to blur at the edges. Some people start to say the ship itself is alive. Others insist that Earth was never real, that it was always a spiritual concept, a metaphor for paradise lost. By generation 100, there might be entire religious movements built around the journey, where the arrival at Kepler 22b becomes not a scientific goal, but a redemptive one, a promised return to Eden or enlightenment. The myth of the mission becomes more powerful than the mission itself. This cultural drift isn't a problem unique to generation ships. It happens in human communities everywhere. But in a sealed vessel travelling through the void, it happens faster and more completely. There's no external reality to check against. There's no way to call someone on the radio back on Earth and say, wait, I think we're getting the story wrong. The narrative becomes self-contained, self-reinforcing. Children learn from their parents, who learned from their parents, and each retelling introduces small changes, small emphases, small spiritual or political meanings that weren't there before. By the time you're 200 generations in, the technical documentation might as well be sacred scripture. Maybe it is sacred scripture. Maybe the same people who maintain the life support systems do so because they're following the rituals described in ancient texts, and they have no idea that those texts were once repair manuals. But there's something deeper and more dangerous beneath the cultural transformation. There's the question of knowledge itself. Someone has to know how the reactor works. Someone has to understand the chemistry of the air recyclers. Someone has to be able to navigate by the stars, or by the ship's instruments, or by whatever systems guide this vessel across 5,000 years of darkness. Knowledge is fragile. It decays. Libraries deteriorate. Paper crumbles. Digital storage, those hard drives and servers that seemed so permanent when the ship launched, begins to fail after a few hundred years. Magnetic charges leak away. Physical degradation sets in. Even if the knowledge is transcribed carefully, copied and recopied by hand, errors creep in. A single digit changes in a calculation. A word is misread. A concept is explained differently by each person who teaches it. Over 2 centuries, the accumulated errors might mean that no one really knows anymore how to repair the engines, or how to adjust the life support, or how to prevent the slow drift towards system failure. Imagine you are Generation 100. You were born in a corridor, and you will die in a corridor. The walls around you are the same walls your great-grandparents knew. The stars visible through the viewports haven't visibly moved in your lifetime. Your ancestors told stories about Earth, about blue oceans and green forests, about billions of people and cities that stretched across entire regions. But you've never seen a photograph of any of it. The electronic archives degraded decades ago, and the copies made by hand are blurry, uncertain, possibly corrupted by copying errors. You might wonder if Earth was real at all. You know intellectually that the ship came from somewhere, that your great-great-grandparents travelled here from somewhere, but it's abstract. It's a story. The only world you've ever known is this one. Metal walls, recycled air, the constant low hum of the engines. The mission is everything. The mission is meaningless. It's just life. You wake up, you do your work, you maintain the systems that keep you alive, and you sleep. Your children will do the same. Their children will do the same. No one alive has ever touched Earth. No one alive will ever touch Kepler 22b. The journey has become infinite. The destination has become mythical. You're somewhere in the middle of an ocean you'll never see the shore of, sailing toward a horizon that never gets closer, and you've learned to accept that this is simply what existence is. There's extensive research on closed, isolated communities over multi-generational timescales. The historical record shows us that no human institution, no government, no social structure has survived unchanged for more than a few centuries. The Roman Empire lasted roughly 500 years before fragmenting. The Catholic Church is approaching 2,000 years and has undergone radical transformations every few centuries. Nation-states typically last 200 to 300 years before revolution or dissolution. But a generation ship doesn't have the option of revolution. It can't split up and form separate communities. It can't declare independence. There's nowhere to go. 500 to 1,000 people, locked in a metal tube travelling through the vacuum of space, where your only option if you want to rebel is to sabotage the life support systems and kill everyone on board. Yet that option probably seems appealing to someone. The documented psychological risks for generation ships include depression, social breakdown, factionalism, mutiny, sabotage, course alteration, or the decision to stop. Some researchers have speculated that a generation ship might not survive the political pressures of its journey, that a crew might decide 50 generations in that they don't want to continue to a destination that's still 2,000 years away. They might vote to stop, to establish themselves in some relatively empty region of space and declare the mission over. Or a faction might seize control and alter course, aiming at a closer star system instead. Or the ship might simply fragment psychologically into factions that hate each other, but have no means of escape from one another. Imagine the psychological stress of living next to someone you despise, in a space you share, with no option for separation, for your entire life, and then passing that stress to your children. Governance becomes the unsolved problem. How do you structure a government that will hold stable for 5,000 years? How do you prevent despotism? How do you prevent factional conflict? How do you make decisions that generations won't challenge? There are no answers. Democracy might fragment into factionalism. Authoritarianism might become oppressive. Meritocracy might calcify into inherited privilege. The children born on the ship are inheriting something their parents never chose: the isolation, the mission, the endless forward motion toward a destination they'll never see. They're inheriting it from parents who volunteered, which makes it feel like an imposition. Biological inheritance, the genetic damage from radiation, the adapted bodies, the altered genes, is bad enough. But psychological inheritance might be worse. By the time your descendants arrive at Kepler 22b, they might not be the kind of people you would have wanted to find the new world. They might be broken. They might be traumatized. They might be fundamentally altered by the experience of being born and raised in confinement, in isolation, in a space that never changes, with a sky that never shows stars, on a journey toward a home they've never chosen. The physics of the journey are brutal, the biology is harsh, but the psychology might be the real killer. Unless, of course, there's a way to skip it. Part 10. The sleep that might not work. Every major science fiction film that deals with interstellar travel uses the same narrative shortcut. In Alien, the Nostromo's crew is in cryogenic sleep for most of the journey. In Interstellar, the crew uses a rotating spacecraft, but the assumption is that future technology will solve the problem. In Passengers, most of the crew is in suspension pods for the journey, waking only briefly near the destination. The narrative problem of 5,000 years of isolation, 5,000 years of radiation damage, 5,000 years of psychological erosion, all of it disappears the moment you introduce cryogenic sleep. The crew goes to sleep, the ship flies on. They wake up at the destination, and it's tomorrow. The question is this actually possible? Is the science real, or is it the biggest false hope in interstellar travel? The current reality of human cryopreservation is not encouraging. We don't have cryogenic sleep technology. What we have is therapeutic hypothermia, a medical procedure where, in cases of severe injury or cardiac arrest, doctors reduce a patient's core body temperature to around 30 degrees Celsius, 5 to 7 degrees below normal. This induces a torpor-like state where metabolic rate drops dramatically, brain function is suppressed, and the body requires much less oxygen and energy to survive. The record for continuous human therapeutic hypothermia is about 14 days. A patient survived continuous cooling for that duration and was successfully rewarmed. It's an extraordinary feat. It's also impossibly far from 5,000 years. The European Space Agency and NASA have been funding research into extended torpor through projects like the Theseus initiative, specifically designed for Mars missions that might last 10 to 15 years. The goal is to develop technology that would allow crews to enter a torpor state for extended durations, perhaps several years at a time, reducing the psychological burden of the journey by essentially skipping the time that passes. The technology doesn't exist yet. Current estimates suggest human trials for extended torpor might begin 10 to 15 years from now. Operational systems for multi-year torpor are probably 20 to 30 years away, if they become possible at all. Multi-century torpor is not on anyone's roadmap. Here's the biological problem with prolonged freezing. Humans don't naturally hibernate. We don't have the physiological adaptations that hibernating animals have. A hibernating bear's biology is specifically tuned to survive months of torpor. Humans are not. Even a single degree of fever can cause serious injury to human tissues. Prolonged hypothermia causes proteins to misfold, enzymes to denature, cellular structures to fail. Ice crystals form in cells, rupturing them from within. The longer you're frozen, the more damage accumulates. To survive being frozen for an extended period, you'd need to prevent ice crystal formation, prevent protein denaturation, preserve cellular structure despite extreme cold, and then somehow restart all of it without damage. The technical requirements are staggering. We're talking about a level of biological engineering we haven't approached. Even if you solved the freezing problem, even if someone figured out how to put a human in torpor for a century, there are new problems. Radiation damage doesn't pause while you're asleep. Your DNA can't repair itself if your metabolism is shut down. The radiation your ship accumulates during your frozen state still reaches you. You wake up after 100 years of sleep with 100 years worth of radiation damage accumulated in your cells. Your muscles and bones are still deteriorating. You can't exercise while you're in torpor. After a century of sleep, you're waking up with the muscle and bone density of an ancient person. Your cardiovascular system has atrophied. Walking will be agony. There's also the psychological trauma of waking. Imagine waking up after 100 years in suspension. Everyone you knew is dead. Everyone they knew is dead. The culture you knew is gone. Languages have changed. Technologies you were familiar with are now historical artifacts. The world has moved on by a century. Repeat this 4 or 5 times, and you're approaching the destination with a crew that has suffered repeated severe psychological shocks. Some proposals address this through a rotation model. 20% of the crew is awake while 80% is in torpor. Every decade they rotate. The awake crew goes into torpor and a new group wakes up. This reduces the psychological burden of continuous isolation, but it requires consistent decade-long torpor technology, which we don't have and might never have. The other issue is that even if you could achieve successful cryosleep, you'd still need to carry the massive infrastructure. The freezing equipment, the life support for the torpor systems, the reanimation equipment, the power to run all of it. You're not actually saving much mass. You're trading continuous crew life support for sophisticated cryogenic equipment. The mass budget barely improves. And there's one more thing nobody talks about. If your cryogenic systems fail, and they will eventually fail over 5,000 years, your crew dies. All of them. No backup plan. A generation ship with continuous habitation can potentially repair systems, maintain things, innovate around problems. A generation ship full of frozen people has no such option. The psychological appeal of cryosleep is obvious. It's the fantasy that you can skip the hard part. You can avoid the isolation, the radiation damage accumulation, the generational trauma. You just go to sleep and wake up when you're there. The problem is that the science doesn't support it, and the technology is decades or centuries away from even being attempted on humans. But there's no alternative. You can't fast forward 5,000 years. You can't make the journey shorter. You can't hide from the radiation or the isolation or the psychological weight. If you send a ship to Kepler 22b, the crew experiences every second of that 5,000 years, whether they're awake for it or not. So here's what you have. A destination that might not be an Earth-like world at all, but an ocean-covered mini-Neptune with crushing gravity and atmospheric pressures that would destroy human lungs. A distance of 640 light-years, requiring journeys measured in the millions of minutes. Propulsion systems that either don't exist or consume impossible amounts of energy. A medium between the stars filled with radiation and debris that slowly damages everything it touches. Human bodies that transform over generations, adapted to weightlessness, fragile, scarred by radiation exposure. Human minds isolated for 200 generations in a metal tube, without conversation, without hope of rescue, watching the mission transform from a shared human endeavour into something approaching religious dogma. And a sleep technology that's supposed to save you from all of this, but probably doesn't exist, and probably never will. Which raises a question that goes beyond Kepler 22b. Has anyone, anywhere in this galaxy, ever solved this? Is there a civilization somewhere that figured out how to cross the interstellar gulf? How to send a ship or a probe or some kind of message across 600 light years? And what if the answer, when you really think through the numbers, is no? What if the distances are too vast? What if every civilization that arises on every habitable planet is forever trapped, forever prisoner to its own star system, forever unable to reach the other lights in the sky? What if the great silence of the universe, the fact that we haven't detected any radio signals from other civilizations, is actually the sound of isolation? Billions of planets, billions of potential civilizations, none of them able to reach any other, all of them alone. That's the question the terrifying journey leaves you with. Not whether we should go to Kepler 22b, but whether anything, anywhere, ever could. Part 11. The Great Filter of Distance. We covered a lot of ground tonight. We learned that Kepler 22b probably isn't a second Earth waiting for us. It's more likely a world of endless ocean, maybe shrouded in clouds, its atmosphere thick and unfamiliar. We learned that getting there would take our fastest theoretical spacecraft 5,300 years. which means we'd need to solve problems we've never solved, keeping humans alive across 200 generations, protecting them from radiation that accumulates like a slow poison, maintaining a social order across centuries of people who never chose to be there, all while travelling through an interstellar medium that's actively hostile, not dramatically but relentlessly, patiently hostile. We learned that cryo-sleep, that reliable tool of science fiction, doesn't actually work. The best we've managed is 2 weeks. We learned that the body itself becomes the enemy on a journey that long, that bones dissolve and muscles atrophy, and the mind, given enough isolation and enough time, can fracture in ways we're only beginning to understand. We learned that even if we managed all of that, if we somehow built a generation ship that held together and held its crew together, we'd arrive at Kepler 22b to find a world we can't live on without massive technological investment, if we can live on it at all. We learned that the closer we look at this problem, the less it looks like a problem we can solve. It looks more like a problem that's fundamentally unsolvable. And so tonight, we have to ask a bigger question. We have to ask where everybody is. This is the Fermi paradox reframed, and I think we've been asking it wrong for 70 years. The classic version goes like this. The universe is vast and old. Life seems to arise wherever chemistry allows it, and yet we see no sign of extraterrestrial civilizations, no signals, no artifacts, no visitors, no evidence anyone else is out there. So where is everybody? Where are all the aliens? The usual answers are interesting. Life might be rarer than we think. Maybe the chemistry of carbon-based biology is harder to arrange than our optimism suggests, and we're a statistical fluke in a sterile universe. Or civilizations might destroy themselves. Self-annihilation through war or environmental collapse or engineered plague might be the default outcome. That's called the Great Filter, and it's genuinely terrifying if you believe it. It suggests we might not make it either. Or there's the zoo hypothesis. Maybe advanced species are out there, watching, but they've decided not to interfere with the younger civilizations. Maybe the universe is full of life, but it's hidden, staying silent, waiting for us to develop enough to earn contact. These are all reasonable answers. We've explored some of them in other videos, but tonight I want to propose something simpler, and I think it might be more terrifying than any of those alternatives. What if the answer isn't biological? What if the answer isn't philosophical? What if the answer is physics? What if every civilization in the galaxy, every thinking species that ever looks up at the stars, faces exactly the same problem we do? What if the distances are simply too great? What if the natural quarantine is distance itself? Think about it mathematically. The Milky Way is roughly 100,000 light-years across. There are an estimated 200 billion stars. Let's say life emerges at a steady rate. Let's say 1 in 1,000 stars develops intelligent life. That would give us roughly 200 million intelligent species scattered across the galaxy. 200 million separate civilizations, each one asking the same question we are right now. Each one looking up and wondering. Each one stuck. Because here's what we know now, after tonight's conversation. Here's what the physics actually allows. If the best technology we can theoretically build with our current understanding of physics, the Daedalus design, running on nuclear pulse propulsion, the most optimized interstellar spacecraft humans have ever designed, takes 5,300 years to reach a destination 640 light-years away, then that's not a problem with our engineering. That's the baseline. That's what's possible at 12% the speed of light. That's as fast as the laws of thermodynamics will let us go. And that means every civilization faces the same question. Do you spend the equivalent of your entire industrial civilization's output to send a ship to another star? A ship that won't arrive for thousands of years, to a world you might not be able to live on, knowing you'll never hear from them again? Do you do this once, or do you do it hundreds of times, committing your species entirely to an exodus with no guarantee of success? The generation ship paradox becomes even more bitter when you zoom out. The technology to build a generation ship, the life support systems, the closed-loop ecology, the medical technology, the computational power needed to navigate and steer and manage such a vessel. The technology to build all of that might also enable faster propulsion. A generation ship that launches today might be overtaken in 500 years by a faster vessel that leaves tomorrow using better technology. So is there ever an optimal time to launch? Is there ever a moment when you think, yes, this is as good as it will get? Or do you wait forever for the next breakthrough, the next improvement, and never go at all? And while you're waiting, other civilizations are facing the same equation. They're building their own ships, facing their own dilemmas, reaching their own conclusions. Maybe some launch and arrive at worlds that are somehow hostile or already inhabited. Maybe some launch and lose contact after a few decades and vanish. Maybe some never launch at all, deciding that the cost is simply too high, that their civilization should turn inward, perfect their own world, and call that success. Meanwhile, the light from Kepler 22 travels. It's been travelling for 640 years already. It will keep travelling, indifferent to whether we ever see it, indifferent to whether we ever decide to reach that star. That star will burn for billions of years. Its planets will orbit in their regular patterns. Kepler 22b will continue its orbit, completing its year in 289.9 days, again and again, whether or not anyone ever gets there. If intelligent life emerged on Kepler 22b tomorrow, or emerged there 500 million years ago, it would face the same problem. Its scientists would look outward and see the Milky Way in all its glory. They'd catalogue thousands of stars within reach of their telescopes. They'd detect some of them. Maybe they'd pick up Earth's radio signals, degraded but detectable, travelling backward through time to touch their planet. They'd think about launching their own ships, and they'd realise what we're realising right now. That reaching even the nearest star takes more time than most species can contemplate, more resources than most can commit, across generations of people who will never benefit, never know if the mission succeeds, never hear the voices of the people they're trying to reach. So the Fermi paradox might not be a mystery about why we don't see intelligent life out there. It might be a statement about the geometry of the universe itself. The universe contains worlds where life might emerge. It contains billions of them. But the distances that separate those worlds create a perfect isolating medium. Every star system is an island. Every civilization is trapped on its own island, looking across a gulf of space that's too wide to cross. There's a bitter kind of poetry in that. The universe shows you paradise. It shows you worlds orbiting distant stars, worlds in their habitable zones, worlds that might harbour oceans and life and civilizations just like ours. And then it makes sure you can never reach them. Not because of biology or warfare or some cosmic conspiracy, just because of the raw geometry. Just because spaces are so large and light is so slow and everything is so far away. Sometimes I think about the planetarium hypothesis. It's an old science fiction idea. Maybe the universe isn't real the way we think it is. Maybe it's a simulation or a construct, and the reason it shows us distant stars that we can't reach is because rendering them is economical. Distance becomes a render distance. The universe shows us the stars, but if we ever tried to reach them, we'd find something wrong. We'd reach the edge of the map. But that's unfalsifiable. We can't test it. We can't know if it's true, and I think that's why the idea is so seductive. It lets us blame something external. It lets us pretend that there's a reason, some cosmic architect who decided this wasn't fair. But maybe the truth is simpler. Maybe there is no architect. Maybe the universe just is. Stars are separated by distances we can barely comprehend. Light takes years and centuries and millennia to travel between them. No civilization, no matter how advanced, can change that. We're not special for being unable to cross these distances. Every species faces the same problem. The universe is built at a scale that isolates every thinking species on its own island of warmth, surrounded by light that comes from stars they'll never reach. That brings us back to Kepler 22b. That's where we started. That's where our conversation tonight has been building toward. So let's go there now. Part 12, The Beautiful Prison. Kepler 22b is still there. It's still orbiting its star right now as you're listening to these words. It completes its orbit every 289.9 days. That's its year. And every single day of every single year, something is happening on that world. If it has an ocean, waves are moving. If it has an atmosphere, wind is blowing. Clouds might be forming and dissolving. If there's life, something is growing, feeding, dying, being born. The world is real and complete, and it's doing all of this whether or not we're watching, whether or not we'll ever arrive, whether or not we even decide to try. But I want to sit with something tonight. I want to sit with the fact that we can see it at all. Earlier tonight, we asked a lot of difficult questions about Kepler 22b. We asked whether it's actually habitable, and the answer is probably not, at least not for humans without radical technological intervention. We asked if we can reach it, and the answer is not with technology we have, and probably not with technology we'll ever have. We asked if the journey would kill us, and the answer is yes, it would. It would kill us with radiation, it would kill us with time, it would kill us with distance and isolation, and the simple fact that a human life isn't long enough to cross the space between stars. It would kill our bodies slowly and our minds with it. We learned a lot of hard truths tonight. We learned that the nearest star system to us, Alpha Centauri, contains worlds we probably can't reach, at distances where even our fastest theoretical spacecraft would take centuries. We learned that travel between stars isn't like travel across an ocean. It's not like travel between continents. It's not even like travel to the edges of our solar system. It's something else entirely. It's slow and it's dangerous, and it requires solving problems that don't have solutions yet. We learned that every propulsion technology we can theoretically build takes thousands of years. We learned that the space between stars is hostile. Not evil, not intentionally cruel, just hostile. It's full of radiation and dust and gases that will sand down your ship and poison the people inside it. We learned that the human body, that miraculous system of 70 trillion cells working in coordination, starts falling apart when you take it away from Earth's gravity for too long. The bones thin, and the muscles weaken, and the cardiovascular system spirals into dysfunction. We learned that the human mind, that consciousness that makes you you, might not survive the isolation and the timescale, and the knowledge that rescue will never come. We learned that the few ways we've thought of to solve this problem, cryogenic suspension, rotating habitats, genetic modification, either don't work or raise questions we don't know how to answer. We learned that the Fermi paradox, that old question about where everybody is, might have a simpler and more fundamental answer than we usually admit. The answer might just be distance. The universe might contain hundreds of millions of intelligent species, and they might all be trapped exactly where we are, on their own worlds, looking up, unable to reach the stars they see. So what do we do with that? I think the first thing is to let go of the catastrophe narrative. This isn't a failure. The universe isn't cruel for being big. The laws of physics aren't malevolent for enforcing speed limits on light and making distance expensive in time and energy. This is just how things are. The universe is indifferent. It doesn't hate us. It doesn't want us to suffer. It simply doesn't care. And there's something almost peaceful in accepting that. The second thing is to remember what we actually accomplished. On a small rocky planet orbiting a medium-sized star in an unremarkable region of a spiral galaxy, there emerged a species that could think. We learned to look up. We built instruments. We pointed them at the sky and we asked questions. And then, and this is the remarkable part, we figured out how to detect the shadow of a world 640 light-years away. We figured out how to measure the tiny wobble in a star's position as a planet orbits, or the tiny dimming in its light as a world passes in front of it. We turned that data into knowledge. We calculated orbits and distances and positions. We concluded, probably correctly, that somewhere out there is a world in its habitable zone, maybe a world of water, maybe a world where life could exist. That's not a failure. That's extraordinary. Think about what that means. We are a species that emerged on the third rocky planet from an average star. We had no instruction manual. No species before us had done any of this. We figured it out ourselves through curiosity and mathematics and the stubborn insistence on asking questions. And we figured it out well enough that we can reach across the galaxy with our eyes. We can see worlds 640 light years away. We can know they're there. For most of human history, we thought we were alone in the universe. We thought Earth was the center and the stars were decorations on a sphere around us. Then we figured out that the Earth orbits the Sun. Then we figured out that the Sun is just one star among billions. Then we figured out that those stars have planets. And then we figured out how to detect those planets. All of that came from the same place, from a species deciding to look, to think, to ask hard questions and follow the answers wherever they lead. Maybe reaching Kepler 22b isn't the point. Maybe the point is that we can see it. Maybe the point is that we tried. Maybe the point is that even though we're separated by distances that seem designed to keep us apart, we can still communicate with light. We can still signal across the void. We can still reach out with our knowledge, even if we can't reach out with our bodies. And here's something I want you to think about. Somewhere out there, if there's intelligent life anywhere in this galaxy, they're probably doing the same thing we are right now. They're looking at their telescopes. They're detecting planets around distant stars. They're calculating distances and building models and asking whether they could ever get there. They're feeling that same pull between wonder and impossibility. They're looking at a world 600 light years away and asking, is anyone there? And they'll never know, because the distance is so great that even light, the fastest thing in the universe, takes longer to travel between us than human civilizations typically last. But that light is still traveling. Right now, photons are crossing the gap between us and Kepler 22b. Light from that star left around 1386 on Earth. That was before Columbus, before the printing press, before the telescope was invented. Light from Kepler 22 was already on its journey. It travelled for 640 years through the interstellar medium. It crossed through regions of space filled with dust and radiation and the remnants of dead stars. It passed through the edges of our solar system. It pierced through our atmosphere. And it's falling on this planet right now. It's falling on the ground beneath your feet. It's reflecting off the surfaces of things. Maybe it's falling on your eyes, carrying information about a distant star, carrying it across the void of space to you. That's not nothing. That's not a failure. That's a connection. That's a message from 640 light years away, travelling through the darkness, touching you. Kepler 22 is sending us information. We're just not capable of sending anything back. We can see the stars. We can know they're there. We can calculate their distances and categorize their light and dream about their planets. We can theorize about what life might exist on those worlds. We can imagine what it would be like to stand on Kepler 22b, to feel alien sunlight, to breathe air processed by an alien ecology. We can wonder about it. We can think about it. We can wonder whether anyone up there is wondering about us. But we can't reach them. Not for thousands of years, if ever. Not with our current understanding of physics. Not in any time frame that would be meaningful to a single human life. The gulf is just too wide. The time is just too long. The obstacles are just too fundamental. And maybe that's the secret message the universe is sending. Not cruelty. Not indifference, exactly. Though there's some of that. Maybe the message is, look, appreciate, wonder, but stay. Stay on your world. Make it beautiful. Make it survivable. Make it a place where life can flourish. Because that's the work you can do. That's the world you can change. The other stars will keep burning. The other planets will keep orbiting. The light will keep travelling. And you can receive it. You can study it. You can learn from it. But you don't need to reach it to make your life meaningful. Kepler 22b is still there, completing its orbit, moving through space at the same velocity as its star, separated from us by a gulf of darkness and time. And somehow, that's okay. Somehow, that's enough. The world exists. We know it exists. We can dream about it. We can point our telescopes at it. That's more than almost any species in the universe will ever get. The knowledge that there are other worlds, other possibilities, Are the chances for life to spark and grow and think? The Fermi paradox asked us where everybody is, and maybe the answer is they're there. They're on their worlds, looking at their stars, wondering about us, wondering if anyone out there is wondering about them. Separated by distances we can't cross, connected by light we can receive. Alone together in the universe, all of us trapped on our islands of warmth, all of us seeing the same beautiful, unreachable sky. That's where we'll leave it for tonight. Kepler 22b is out there, orbiting its star under its alien sky. The photons from that world are travelling toward you. The mystery remains, the distance remains. And somewhere in that impossible space between the stars, there's something beautiful. There's the evidence that the universe is far stranger and far more interesting than we ever imagined, and we're here to see it. Sleep well tonight. Dream of oceans on alien worlds.